There are some reactions we call equilibria. A reaction that is balanced, we say, is in equilibrium. And these reactions are very important to biological functions. Biological systems are controlled by reactions that are equilibria. In fact, you could consider your body to be billions and billions of equilibria that are all tied to each other so that your life is in balance and continues to function properly. When an equilibrium is disturbed in your body, it often will have catastrophic effects. So it's important that we understand what equilibria are and how they are affected. Some reactions are reversible. We've been looking at reactions that are displayed as going in the forward direction only. But some reactions will go forward and go in reverse. Now, you're mostly familiar with those that go spontaneously in the forward direction, like the combustion of wood. You've never seen carbon dioxide and water reform to make wood. It's done in order to make wood, it has to go through another process of having a tree take carbon dioxide and water and using sunlight to reform them into glucose, which then is assembled into cellulose, that is the major component of wood. But some reactions are spontaneously reversible. For instance, if I take a cup of water and put it in a cup of sugar, you will have some of the sugar will dissolve, but some of it will not. As it sits there, more of the sugar will dissolve, but some of the dissolved sugar returns to the solid state. And this is called an equilibrium. We show an equilibrium reaction with a double arrow to indicate that it is a reversible reaction. There's a forward reaction and there is a reverse reaction. So at the same time that sugar is dissolving and becoming aqueous sugar or dissolved sugar, we have aqueous sugar returning to the solid phase. And we call this a steady state when we reach what is called equilibrium. Equilibrium is when a system appears not to be changing, but there's much activity occurring at the molecular level. There's a forward reaction and a reverse reaction occurring, but there's no noticeable change in the system. In the sugar in water system, the sugar solid is staying solid. It appears to be staying solid, but what you can't see is at a submicroscopic level, the molecules are going from the solid state into the aqueous state and then from the aqueous state into the solid state. But your eye cannot see that. Even with a microscope, you would not be able to see that. Other examples of equilibrium that you may be able to relate to are things like your bone mass. In a year's time, my bone mass may not change, but there are cells in my body called osteoclasts that are constantly breaking down my bone mass, and then there are cells called osteoblasts that are constantly reforming my bone. What happens is that my bone is constantly being broken down and reformed over time, but the essential amount of my bone mass does not change. Again, this is an equilibrium. Equilibrium systems appear not to be changing. They are what we call a steady state reaction. There's a lot of reaction ongoing, but the concentrations of the reagents and products are staying the same. We use a double arrow to indicate that there's both a forward and a reverse reaction, and equilibrium is defined to be when the rate of the forward reaction equals the rate of the reverse reaction. What we're going to be doing is looking at how will equilibrium change as you make changes. Just as a teeter-totter is at equilibrium, balanced, When you make a change to it, like adding a weight to one side, what you find is its balance or its equilibrium changes. Chemical systems are very similar to this in that what happens is that you can make a change to an equilibrium. We call it stressing the equilibrium, and that stress causes it to find a new equilibrium position. Here's an example of an equilibrium. In liquid water at room temperature, what we find is tiny amounts of the water are breaking apart and making a hydrogen ion, called a proton sometimes, and a hydroxide ion. The concentration of these do not change, but there's constantly ongoing water breaking apart to make a proton and hydroxide, and then protons and hydroxide reforming to make water. The number of protons and hydroxide concentration, the concentration of those remains steady. The amount that is formed is equal to the amount that recombine and produce water. It's very dynamic, but it is a steady state. Because we see the double arrows, we recognize this as an equilibrium. What kind of changes will affect a chemical equilibrium? It's the same things that affect the rates of reactions. We will see that equilibria are affected by reactant and product concentrations, by temperature and pressure and catalysts. The most important one is concentration of reactants and products. We're not going to investigate temperature and pressure because we just don't have enough time for that in this course. So we're going to emphasize how equilibria are changed by the constant changes in concentration of reactants and products. Let's look at this equilibrium again. We have water breaking apart to make protons and hydroxide and protons recombining to make water. If I add hydroxide to this system, what happens is there's more hydroxide in the system and they have more opportunities to bump into protons. With the more opportunities to bump into protons, what happens is the reverse reaction speeds up because we've increased the concentration of hydroxide. This causes the concentration of protons to decrease. Likewise, if I add protons, the concentration of protons increases and the chances of protons combining with hydroxide increases and the rate of the reverse reaction increases. So what we see is that when we change the concentration of one component of an equilibrium, the other will also change. The amount of protons decreases as hydroxide is added. Likewise, the amount of hydroxide decreases when the amount of protons is increased. Let's look at this reaction. If I put ammonia in water, what I find is it forms ammonium and hydroxide in solution. What happens when I add more ammonia to the water, to the solution? The amount of ammonia has increased so that it has more opportunities to combine with the water. The amount of water then decreases and the amount of ammonium and hydroxide increase. Now I'm introducing in this slide a little shorthand that we have in chemistry, which is to use brackets to indicate concentration of. Anytime you see a bracket around a molecule or an ion, it's saying concentration of that particular substance. It actually means concentration in molarity, but we haven't gone into molarity yet, so you don't have to worry about that. So as you see brackets, just replace the brackets in your head with concentration of. So when I add ammonia to a system, the concentration of the water, which is with it on the same side of the reaction as the ammonia, goes down, and the concentration of the ammonia and the hydroxide, which are on the opposite side of the reaction, go up. This goes into a little rule of thumb that we have. We actually call this Le Chatelier's principle. Le Chatelier's principle states that an equilibrium will respond to a change made to it so that it lessens some of that change. Well, what we're going to do is we're going to use this a little simpler way of phrasing this, and we're going to make it very practical. We're going to say, if we add a component of a reaction, it must be an equilibrium now. If we add a component of an equilibrium, the concentration of the components on the same side of the reaction decrease, and the concentration of the components on the opposite side of the reaction increase. Likewise, if we remove a component, the concentration of the components on the same side increase, and the concentration of the components on the opposite side decrease. This is a very practical way of stating how concentration will change in equilibrium using Le Chatelier's principle.
Here's an example of an equilibrium, and we're going to see how changes will play out in the position of the equilibrium. The first thing to notice is that there is a double arrow there. That means a reaction forward and a reaction in reverse. A double arrow is indication of an equilibrium. Next, we notice that we have acetic acid, that's the compound to the left, plus water is going to give us acetate and the hydronium ion, H3O+. So I'm looking at the components of the equilibrium. I've read through them and I understand them. I see that there is an aqueous after all the components except for water. Water is a solvent here because it says aqueous. That means there's a huge amount of water compared to the other components. Now, if we look down at the changes that we're going to make, you can see some of them are in color. Or all of them are in color, really. But you can see they're in different colors. This is because I'm going to separate in my analysis of this my action on the equilibrium from the reaction, or from the response of the equilibrium. It is most useful to analyze equilibria this way, to say, what am I doing to the equilibrium, and then separating it and saying, well, this is how the equilibrium responds. So let's look at the first one. It says to add acetic acid. That's my action on the equilibrium. So my action on the equilibrium is that acetic acid will increase, and we see that increase when we add it to an equilibrium. The response is that what's with it will go down and what's opposite it will increase. Well, water is what's with it, but it's a solvent and there's a huge quantity of water. What's with it will go down, but the amount that goes down is infinitesimally small compared to the amount of water. So we're not even going to worry about what's happening to the concentration of water. Yes, a tiny amount is being consumed by the increase of acetic acid, but we wouldn't be able to measure it. What's opposite your increase, though, will also increase. So what's with it goes down, what is opposite increases, so acetate and the hydronium ion will both increase. We go to the next change, add acetate. So my action on the equilibrium is that I'm increasing my acetate concentration. In response, the equilibrium will have what's with it go down and what's opposite it go up. And so we see the hydronium ion concentration decreases and the acetic acid concentration increases. If I add hydronium ion, that's my action on the equilibrium. The reaction of the equilibrium is that acetate goes down and acetic acid goes up. If I remove hydronium ion, my action on the equilibrium is that the hydronium ion concentration decreases. So what's with it will build up, and what's opposite it will decrease. If I add sodium chloride, I look at my equilibrium and I cannot find sodium chloride anywhere in that equilibrium. As a result, I know I can conclude there will be no change to the equilibrium. because only if something is participating in the equilibrium will it be able to change that equilibrium.
It's your turn to try it. Go ahead and pause the lecture and try to figure out how the equilibrium will respond to each of these changes.
Okay, the first change is that we're adding ammonia. So my action on my equilibrium is that that increases. The reaction of the equilibrium is that what's with it will go down and what's opposite increases. Nothing is with it, so what opposite is increases is the only response the equilibrium has. If I add hydrogen, I will see that my action on the equilibrium is that hydrogen increases. What's with it will go down, so nitrogen goes down, and what's opposite increases, so ammonia increases. If I add nitrogen, my action on the equilibrium is that nitrogen increases. What's with it will go down, so hydrogen decreases, and what's opposite will go up, so ammonia increases. If I look at add nitrogen dioxide, I can see there's no nitrogen dioxide in the equilibrium. What you're adding has to exactly match what's in the equilibrium, and dinitrogen monoxide does not match nitrogen nor ammonia or the hydrogen, so there is no change on the equilibrium. Be sure to do problems. There are index problems that you can do as you read, and be sure and do these end of chapter problems. Notice, equilibrium is not in the textbook. As a result, the worksheet problems are going to become very important. Those will be the only problems you will have to try. Also, you will need to do the online quizzes, of course, and they will have some online, the online quizzes will have some equilibrium problems to do.